I will probably give you all your next homework assignment tomorrow, probably be two, a week from Friday. That's what it looks like, so. We're talking about separability. Let me recall for you that separability is first defined as polynomials. An irreducible polynomial will be field is separable if, when you go to a splitting field or a splitting field of it, it factors into distinct linear factors. The distinct is the important thing here. And an element, we call an element separable if, well, say an element that's algebraic of the field K, say. We say the element U is separable if, when you look at its minimal polynomial over K, it's a separable polynomial. So let's get kind of the first cool thing about separable. We're going to prove this first, and then we're going to weigh up the voltage for the next one. This result's kind of classical. Let hand side have to be fields, the element U and F, say algebraic. Yeah. With minimal polynomial. Fx Ax is separable over K. If and only if the GCD of f of x and its derivative is 1. I'll press sometimes refer this to the formal derivative because it's basically math 1020 derivative, right? Where you just bring the exponent down, blah, blah, blah. There's no notion of limits here in creation of this thing. It's nice to see the derivative showing up in the context. Proof. Let's go this way first. If f of x is not separable, that means that its polynomial must be a form u minus. So for some n bigger than 1. So in other words, this thing has to have a multiple root. That multiple root, nobody said necessarily has to be u, but there's some multiple root. Now, if you notice, okay, I'll press, hold on to your seatbelts because it's time for a changeable. This is And so notice that, you have a, common factor. That is to say, since n is bigger than one, a is a root of f of x and f prime of x. So PCD can't be one. By the way, does everybody see why that's true? These are two elements of polynomial. F and F prime are two elements of polynomials. Polynomial.
You know, it's like it's if we have a root, it should be the binomial multiplied by x minus.
Well, right. But I like this kind of. Let me get this paired with that little explanation. A polynomial thing. Is a principal ideal. Over a field. That's straight away. The polynomial ring over a field is the principal ideal domain. So if dx is GCD of f of x and f prime of x, then d of x can be expressed as a linear combination. D of x, f of x, plus h of x, f prime of x. So if a is root of f and f prime, then it is a root of d of x. And of course, the polynomial one has no root, right? So there you go. Okay, any questions on that? Let us go in the other direction. Now, we want to show that if U is separable, then the GCD is one. So again, let's suppose that let's let the GCD of these two things be d of x. And let's suppose that the degree of d is at least one. With degree of d of x at least one. So notice that D has a root in the splitting field of F. Since D of x divides F of x, D of x has a root in the splitting field of f. F of x, okay. And also this root must be shared by both f and f prime. Because again, we've got Jesus identity here. If A, let's call it A, is a common root of g of x and f of x, then it needs to be right. Then it's shared by f prime of x. And so let's write by right. It's really kind of misleading here. I think this is kind of misleading here. I mean, basis identity applies, but the reason this root is shared by this is because d of x also divides f prime of x. So let me write that. F prime of x is alpha of x, d of x. So the root here has to be a root here as well. Okay, back on track. So let A be a root that is shared by both f and f prime. And let's assume that f is separable. Then f of x is x minus a times g of x with a not a root of g of x. But again, with the whole derivative thing here. But now f prime of x is equal to g of x plus x minus a prime of x. Now, a is a root of, if a is shared, a is a root of this, and so if a is a root of f prime, then a is a root of g, which is contradiction. So a is a root of this, so if a is a root of f prime of x, then a is a root of g of x, which is a contradiction. And so this establishes what we want because f of x cannot be a separable polynomial. Okay, any questions? Okay, so this, I'm gonna make this one actually a lot more powerful, in a certain sense. Oh, conversation. Suppose K is a field and f of x is an irreducible polynomial. Suppose f of x and k of x is a polynomial. That's it's not separable. Then derivative of this polynomial is zero. This is key, right? I mean, this is kind of a good thing. Because if it's not separable, its derivative is zero, right? And so that's pretty powerful right here, because of course, the derivative of constants is zero, but the only candidate you never have for separable polynomial is one whose formal derivative is zero. So we'll see why this is true. If f of x not separable, then f prime of x equals zero, or right? I mean, I really don't need the separable descriptor here. If I take the derivative of a polynomial, one of two things happens. Either the polynomial turns out to be zero, right? Or if its degree is defined, because the polynomial, zero polynomial doesn't have a defined degree. The degree is defined, it has to be less than the degree of the original polynomial. Right? Alice, these previous limits, not separable. Uh, the previous lemma, we know that if it's a separable polynomial, greatest common divisor of f and f prime are non-trivial. Uh, 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 I mean, otherwise you can just take a polynomial x minus one squared or something like this. And this is where I knew that I would need it. But f of x is, and so in particular, it's prime. So if because the only divisors of f are itself one, right? Because it's irreducible up to units. The only divisors of f, because it's irreducible, are itself and one. So if the GCD is not one, this has to be this. But derivative has to be zero. Because if it's not zero, then it's got a smaller degree, smaller positive degree, or well, non-negative, and f divides it, which is ridiculous. So the derivative has to be zero. Okay, questions? This is powerful, and it actually, can anybody? Anybody think out what might be an important corollary here? I mean, how many times have you ever taken the derivative polynomial of a zero polynomial? Probably only if it's constant, right? Can anybody name a polynomial whose derivative is not zero? Identically zero. It is not a constant.
An existing P.
That's right. You have to go into characteristic something of zero, right? So this gives the following exciting spin-off. And I promised you this to you before, if K and F is algebraic and characteristic K zero, then K inside F is 17. So any degree z, if your characteristic zero, then any algebraic extension is automatically 7. It suffices to show any irreducible polynomial and characteristic zero. So so suppose that well, let F be irreducible. So that's not acceptable. Then net prime of X is identically zero. But well, it's very detailed for a reason. And here, I guess I could have assumed AM is not zero, because otherwise, why would I have written? But this is this must imply, because this first term has to be zero, which forces M to be zero, which means that the original polynomial constant. It's non-irreducible. In fact, the proof shows exactly. So we'll make this following observation. Because that exists. Thing I'm gonna observe is, if f of x and kx is not separable. Yeah. The characteristic of k and the characteristic of the field has to be p, for p some positive prime. And what's the general form of a polynomial that is whose formal derivative is going to be zero in this situation? Must be a polynomial next. Because really, what you need to make the formal derivative go away is you need that every exponent has to have a factor, p, right? For some. Well, it has to be sort of a polynomial next to p. And that way, formal derivative is zero. So these are my usual suspects, right? So, for example, if you're in characteristic 2, and if you look at the polynomial x squared plus x plus 1, then I wouldn't expect that to be so. In fact, if you look, let's just look at the quadratic polynomials. Okay, so now I'm looking at polynomials over F2. Which of these polynomials are separable? Which of them are not separable? These two have formal derivative 0, don't they? But they don't really fall under our definition of separable. Why? They're not irreducible. And this is a little bit more obviously not irreducible, right? So, yes, these have multiple roots, but they don't count as they're not irreducible. This one's not irreducible either, is it? This one is the only irreducible polynomial in grade 2 elements. What's its formal derivative? 1, right? And so clearly it is relatively prime to its formal derivative, right? GC is 1. So this is actually a separable polynomial. Actually, it's kind of interesting. We'll see this later. Any algebraic extension, any algebraic extension in characteristic 0 is automatically separable, and any finite extension of a finite field is also separable. So where are you going to find these interesting algebraic extensions? They're not. It has to be an infinite field of positive characteristic. Okay. So let's start sort of classifying these in a more specialized way. Definition. K and F be an extension of fields, an element U and F is purely inseparable. Okay. Here, it's minimal polynomial. Is the form X minus U, But I mean, maybe that's as inseparable as it gets, right? Because it's a single linear to some power, right? There's no kicker polynomial. You will. F is a purely inseparable. Okay. If every element you have is purely inseparable. Example. Let's just let K be C mod EZ. And apologies to all you PA fans out there. I am a lazy fellow. Then consider KX this is rational functions in variable X. This is rational functions in variable X P. Notice that actually before I get this example, before I get this play, let's call this so I can use X as my polynomial here now. Notice that X is purely inseparable. Over sorry. He is purely inseparable over this because this is in this is a polynomial with coefficients in K adjoint to P. Right? And notice that this thing is equal to sure you all seen freshman's dream. So this is actually the characteristic P that's workable. So notice that this element is purely inseparable. I made the claim that this is the minimal polynomial, and that is true. Let me go through it. First of all, it doesn't matter if this is the minimal polynomial or not, because the minimal polynomial will be of the form x minus t to the m, where m is less than or equal to p. Right? But it's fairly easy to see that this is minimal polynomial because for example, if you have any exponent less than t, then you have t to that exponent has to be an element of ktp, which is not the case here, right? So this is indeed minimum. Here is a silly observation, but an important one. Theorem. A, F, E, and do an element of that. If both separable and purely inseparable, then what's the conclusion? Except so if you have an element of field extension U that is both separable over K and purely inseparable over K, minimal polynomial of U cause it's purely inseparable is a form x minus U to the M. But if U is separable in one, right? Because you can't have multiple roots. Therefore, x minus U is in kx. So U. Here's another like really kind of groovy theorem. I really like this. Oh, any questions on that? Uh, so. The comedian, but then the comedian's, he's always drinking bourbon on stage. Southern guy. I guess you won't watch higher class stuff than I do. Anyway, so he famously had a comedy routine called "You Can't Fix Stupid," but you can fix inseparability. Is it Ron something? Ron White, that's who it is. You can't fix stupid, but you can fix inseparable. And I'll show you what I mean by that. Theorem 8.7. Let's suppose we have a field extension. Characteristic cadence so characteristic is positive prime. If U is algebraic over K, you may not be, separable. So I just picked an algebraic element at random over field characteristic P, but this is what I mean by you can fix inseparable. U to the P to the N is separable. So. N. So in other words, what you can do is you can take your element to the P power, P squared power, P cubed power, you can keep powering it up by P, and eventually you will get a separable element. It's sort of taking those prime powers, sort of squeezes the inseparability out of it. So you can clean a arbitrary messy element into one that is separable by taking an appropriately large prime power of it. Prime power exponent of it. So okay. And when I say this, what I mean is that's what I mean by the degree of the element over K. I mean, in U over K, or it's the degree of the minimal polynomial. If this is one, then because actually here. How about n zero? Let me throw in zero there, and then if the degree u over k is one, that means that u is already in k, so it's separable. So u to the p to the zero is separable. We're done. If not, let's suppose that f is the minimal polynomial of a non-separable element of degree greater than one. Minimal polynomial of a non-separable element of degree greater than one. Then, what do we know? We've already established that in an earlier theorem. The degree of the polynomial must be zero. And so f is a polynomial. So so x is, or I'm sorry, not x. So f is a polynomial in xp. So what does this mean? U to the p, right? So notice that u to the p is a root of g. And so u to p is algebraic over k. 3 less than 3. So that is this degree. So by induction, the P, the N, which is U, P, N plus one, second. And we're done. Okay, any questions? Here, thank you for it. Suppose that F is an extension of K, characteristic of K again is P. Following. The following are equivalent. Number one, F is purely inseparable of K. The irreducible polynomial of any U and F is of the form its minimal polynomial is a form x n minus a and kx. So every element of F has an irreducible polynomial of that form. If third part of this if U is in F, then U to the P to the N is in K for some n natural number of zero. So if you take a large enough P to the N power element, it lands you down K. The only elements of F that are separable over K are the elements of K. F separable over K are the elements of K. We know all elements of K are separable over K, but in this case, they're the only ones. And finally, F is generated by a set of purely inseparable elements. Any questions? All right. Well, cogitate that well, and we will see you on Wednesday.